Somewhere in the dark between the stars, a world is drifting. It has no sun. It has never had one. It moves through the galaxy in silence, in cold, in a darkness so complete that no eye has ever seen it directly. Welcome to the Sleepy Lab. Tonight, we drift through the science of rogue planets, worlds that belong to no star, that wander the galaxy alone, carrying their frozen surfaces and their hidden depths through billions of years of quiet solitude. We will follow them from their violent beginnings to their long, patient journeys through the dark. And we will ask, very softly, whether alone truly means empty. If this kind of gentle science helps you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. A rogue planet is, at its simplest, a world without a sun. It is a planetary mass object, something with the size and gravity of a planet that orbits no star. It drifts freely through interstellar space, bound only to the slow gravitational pull of the galaxy itself. Astronomers have several names for these objects. Free-floating planet is one. Isolated planetary mass object is another. Rogue planet is the informal term, the one that carries a certain quiet poetry. It is the one that has stayed. You might expect such objects to be rare, exotic exceptions in a universe organized around stars and their orderly systems. They are not rare. Current estimates suggest that rogue planets may be among the most numerous worlds in the entire galaxy. Some models predict there are more rogue planets in the Milky Way than there are stars. Let that settle for a moment, not with alarm, but with a kind of slow wonder. The early evidence came from a technique called microlensing. When a massive object drifts between Earth and a distant background star, its gravity bends and briefly brightens that star's light. The duration and shape of that brightening encodes information about the object's mass. Early surveys using this method suggested roughly 2 Jupiter-mass rogue planets for every single star in the galaxy. More recent surveys have revised that figure somewhat. The precise number remains uncertain, but even the more conservative estimates place the total count of free-floating worlds in the billions. Billions of worlds drifting in the dark. They are extraordinarily difficult to see. A rogue planet receives no starlight, and it emits almost no visible light of its own. It does not shine. It does not glow. It simply moves through the interstellar medium, cold and quiet, leaving almost no trace. The surface temperature of a typical rocky rogue planet is estimated to be around -240 degrees Celsius. That is close to the coldest temperature that physics permits. At those temperatures, most gases do not remain gases. They freeze. Carbon dioxide, nitrogen, even the thin wisps of any atmosphere. All of it would collapse slowly onto the surface, settling as frost. A rogue planet at those temperatures would be wrapped in a silence deeper than anything we experience on Earth. No wind, no weather, no sound of any kind. Just the slow accumulation of frozen gas on a surface that has not been touched by warmth in billions of years. And yet, cold does not mean dead. Despite the frozen surface, rogue planets are not necessarily geologically inert. Inside them, something continues, something slow and steady and ancient. Radioactive decay. Elements like uranium, thorium, and potassium are present in the rock of any planet that formed from the enriched material of the galaxy. And those elements decay, slowly, steadily, releasing heat as they do. This process does not require a star. It does not require sunlight or proximity to anything. It happens in the dark, in the deep interior of a world, regardless of where that world happens to be. This is not a strange or exotic process. It is the same one happening inside the Earth right now, beneath your feet, beneath the oceans, beneath the crust. Radiogenic heat is what keeps Earth's interior molten. It is what drives the slow movement of tectonic plates. It is what makes our planet geologically alive. A rogue planet carries that same fire within it. And for a sufficiently large rogue planet, one with enough mass, enough rock, enough radioactive material that internal heat may be enough to do something remarkable. It may be enough to melt ice. Beneath a thick shell of ice, deep inside a rogue planet drifting through the dark between stars, there could be liquid water, a subsurface ocean sealed away from the cold, insulated by the ice above it, warmed from below by the slow decay of ancient elements. The ice shell itself would act as a blanket, trapping the internal warmth, preventing the water beneath from freezing, holding the ocean in a kind of geological embrace that has nothing to do with any star. This is not speculation without precedent. In our own solar system, Europa, a moon of Jupiter, maintains a liquid ocean beneath its icy surface, far from the warmth of the sun. Enceladus, a moon of Saturn, does the same. These worlds have shown us that liquid water does not require a star. It requires only the right combination of mass, chemistry, and time. A rogue planet could have all three. Drifting through the galaxy, carrying its hidden ocean through billions of years of darkness, it would be a world that has never seen a sunrise and never will. And yet, somewhere beneath its frozen shell, water would move. Slowly, perhaps. Quietly, certainly. But it would move. There is something in that image worth sitting with for a moment. A world in complete darkness. No sun above. No light at all. And yet, deep inside, warmth, water, the slow chemistry of a living interior. The universe, it turns out, has more ways to keep a world warm than we initially assumed. In the dark between the stars, that vast, cold, seemingly empty space is not as empty as it looks. It is populated with worlds we are only beginning to learn to find. Worlds that drift on, patient and silent, carrying their secrets through the long dark of deep time. The ice above that ocean would not simply be a barrier, it would be a blanket, a shell of frozen water, perhaps dozens of kilometers thick, pressing down on the liquid beneath and holding the warmth inside. The colder the surface grows, the more the ice thickens, and the more it insulates. There is a quiet elegance in that arrangement, the very coldness of the universe, working against itself, helping to preserve the warmth below. We have seen this before, closer to home. Europa, one of Jupiter's moons, carries a global ocean beneath miles of ice. The ocean has likely been liquid for billions of years, kept warm not by the sun, but by the tidal pull of Jupiter stretching and flexing the moon's interior. Enceladus, orbiting Saturn, does the same, and it goes further, venting plumes of water vapor and ice crystals into space, as if exhaling. These are not theoretical worlds. They are real places, visited by spacecraft, studied in detail, and they have already rewritten what we thought we knew about where liquid water can exist. A rogue planet's subsurface ocean would be darker than either of those. Europa receives a faint trace of sunlight, even filtered through ice. Enceladus orbits within Saturn's system, touched by reflected light. But a rogue planet has no star. No light reaches its surface from outside, and beneath the ice, there would be nothing. No glow, no gradient, no direction that could be called toward the light. Only the absolute dark of a sealed interior, and the slow movement of water in that dark. Photosynthesis would be impossible. There would be no sun to drive it, no light to capture, no surface where a leaf or a cell could spread itself toward warmth. The entire energy budget of that ocean would have to come from within. And here, the seafloor becomes important. On Earth, in the deepest parts of the ocean, there are places where the crust cracks open and superheated water rises from below, carrying dissolved minerals from the rock. These are hydrothermal vents, and around them, in the complete absence of sunlight, entire ecosystems thrive. Tube worms, shrimp, bacteria, archaea. Life built not on light, but on chemistry, on the energy released when certain minerals meet certain fluids at certain temperatures. A rogue planet with a warm interior and a subsurface ocean could have the same The seafloor of that hidden ocean might crack and shift, driven by the slow convection of the rock below. Warm, mineral-rich water could rise through those cracks, and in the chemical gradient between that warm water and the cold ocean above it, there would be energy, free energy, available to any organism that had evolved the machinery to use it. Some astrobiologists consider this a plausible scenario. Not likely, perhaps, not something we should expect to find, but physically permitted, consistent with what we know about chemistry, energy, and the conditions that life on Earth has already shown it can tolerate. The pressure at the base of such an ocean would be immense. A deep ocean on a world with significant mass would press down with a weight that would crush most familiar structures. But life on Earth has already found its way into high-pressure environments. Certain microbes thrive in the deepest ocean trenches, where the pressure is more than 1,000 times that of the surface. Pressure, it turns out, is not an absolute barrier. It is a filter, selecting for organisms built to endure it. Life on a rogue planet, if it existed at all, would be shaped entirely by its environment. It would have no concept of a star, no sense of seasons, because there would be none. No orbit around a sun, no tilt, no cycle of warmth and cold driven from outside. No concept of a year, because a year is defined by a journey around a star, and this world would make no such journey. There would be no light, no color, no sky in any meaningful sense. Only the rock below, the water above, the heat rising from the deep, and the slow chemistry of survival. Whatever lived there would be defined by patience and darkness and pressure. It would know the world as a place of gradients, warm here, cold there, rich in minerals in this direction, depleted in that one. It would know nothing of the galaxy it drifted through, nothing of the billions of stars burning in the dark above its ice. It would simply be, and that, in its own way, is enough to sit with for a moment. Now, how does a world like this come to exist in the first place? Rogue planets form in at least two distinct ways. Both are thought to occur in nature. Both have left their marks on the galaxy. The first is ejection. A planet forms normally, within a disk of gas and dust orbiting a young star. The same way Earth formed, the same way Jupiter formed. It grows, it settles into an orbit, it becomes a world. And then something goes wrong. The early history of a solar system is not peaceful. The orbits of young planets are unstable, shifting, overlapping in ways that lead to close encounters. When two massive planets pass near each other, gravity does something precise and ruthless. It transfers energy from one to the other. One planet slows, falling inward. The other accelerates, moving faster than its orbit can hold it. And if enough energy is transferred, that second planet reaches escape velocity, the speed at which no gravitational bond can hold it back, and it leaves. It does not explode. It does not collide. It simply goes. Accelerating away from its star, crossing the outer reaches of the system, passing through the cold dark beyond the last planet, and then entering interstellar space. A world fully formed, carrying its geology and its chemistry and whatever history it had accumulated, now alone. Jupiter is thought to have played this role many times in the early solar system. Its gravity is immense, and in the chaotic early period when the giant planets were migrating inward and outward, it likely ejected a large number of smaller bodies, asteroids, comets, and possibly something larger. Some models suggest that a fifth giant planet once existed in our solar system and was ejected by Jupiter's gravity during that turbulent period. If so, it is out there somewhere, a world the size of Neptune or Uranus, drifting through the galaxy, carrying no memory of the sun it once orbited. Computer simulations of planetary system formation reproduce this process reliably. When researchers model the formation of solar systems from first principles, starting with a disk of gas and dust and letting gravity do its work, ejected planets emerge naturally, almost inevitably. They are not an anomaly in the models. They are a byproduct, a consequence of the same gravitational dynamics that build stable systems. For every solar system that settles into a quiet arrangement of orbits, there may be one or more worlds that did not survive the process, that were flung outward in the early chaos and never returned. Those worlds are still out there, moving through the galaxy on the trajectories they were given billions of years ago, carrying the frozen record of their formation, their brief time in a solar system, and the long silence that followed. But ejection is only one way a rogue planet can come to be. There is a second path, and it begins not in a solar system at all, but in the open dark of a molecular cloud. In certain regions of the galaxy, vast clouds of gas and dust collapse under their own gravity. When the conditions are right, a collapsing pocket of material can form a world-sized object, not by gathering around a star, but by condensing on its own, the way a star would, following the same gravitational logic. The difference is mass. A star ignites because it accumulates enough material for the pressure at its core to trigger hydrogen fusion. These objects do not reach that threshold. They collapse. They warm briefly from the energy of their own contraction, and then they cool, slowly, quietly, without ever lighting up. They are sometimes called sub-brown dwarfs, when their mass falls below roughly 13 times that of Jupiter. That number, 13 Jupiter masses, is approximately where sustained deuterium fusion becomes possible, and it serves as a rough boundary in the classification of these objects. Below it, there is no fusion, only cooling, only drift. The name itself points to something interesting. Brown dwarfs are sometimes described as failed stars, objects that form the way stars form, gathered mass the way stars gather mass, but stop short of the ignition point. They're not planets in the traditional sense. They did not form in a disk around another body. They condensed directly from the interstellar medium, alone, following their own gravitational collapse. And at the lower end of that range, the very lowest mass brown dwarfs, the distinction between a brown dwarf and a rogue planet begins to blur. This is not a failure of science. It is a feature of nature. The universe does not draw clean lines between categories. It produces a continuous distribution of masses, and we impose our labels afterward, doing our best to find the seams. But between a very low-mass brown dwarf and a very high-mass free-floating planet, there may be no seam at all, only a gradual transition that our definitions have not yet learned to follow. Astronomers continue to discuss where one ends and the other begins. The honest answer, for now, is that the boundary is soft, a region of overlap rather than a threshold, populated by objects that carry characteristics of both. There is a third origin story, quieter than the others. Some rogue planets may have begun their lives not alone, and not in a solar system, but as companions to stars, binary partners, orbiting at great distance, gravitationally bound but loosely so. Over time, a close encounter with another star, or a slow accumulation of gravitational nudges from the surrounding cluster, could have been enough to sever that bond. The planet, if it was a planet, would have drifted away, no longer held, continuing on a path that now had no anchor. This kind of separation happens more easily in crowded environments. Dense star clusters are particularly efficient at producing free-floating worlds. When stars are packed closely together, gravitational encounters between neighboring systems are far more frequent. A planet orbiting one star may feel the pull of a passing star strongly enough to be destabilized, its orbit stretched, tilted, eventually broken. In a sparse region of the galaxy, such encounters are rare. In a dense cluster, they are almost routine. Globular clusters take this to an extreme. These ancient, roughly spherical collections of stars, some containing hundreds of thousands of suns packed into a region only a few hundred light years across, are among the most gravitationally turbulent environments in the galaxy. Stars there pass close to one another far more often than they do in the open disk of the Milky Way. Any planets that formed in a globular cluster would have faced a gauntlet of gravitational disturbances from the very beginning. The Milky Way contains over 150 known globular clusters. Each one is a potential source of many free-floating worlds, planets ejected over billions of years of close encounters, drifting outward from the cluster, eventually dispersing into the broader galaxy. How many worlds those clusters have released over their long histories is difficult to estimate, but the number is likely very large. And then there is the death of stars. When a massive star reaches the end of its life, it does not simply fade, it collapses and then explodes, a supernova, releasing in seconds an amount of energy that dwarfs everything the star produced over its entire lifetime. The shockwave expands outward at a significant fraction of the speed of light. Any planets that were orbiting that star, worlds that may have existed for millions or billions of years, are suddenly unbound. The gravitational anchor that held them in place is gone, replaced by an expanding shell of hot gas and a rapidly cooling remnant. Those planets do not disappear. They continue moving, carrying the velocity they had at the moment of the explosion, now on trajectories that lead away from the site of the supernova and out into the galaxy. They become rogue planets, not through a slow gravitational negotiation, but through a single, violent severance. Stars in binary systems, two stars orbiting each other, present their own complications for any planets in those systems. As one star in a binary pair evolves, it changes mass. It may expand into a giant, shed its outer layers, or eventually collapse. Each of these changes alters the gravitational balance of the system. Planets that were stable under one configuration may find themselves in unstable orbits under another. Over time, they may be ejected, not by a dramatic explosion, but by the slow, patient arithmetic of orbital mechanics responding to a shifting gravitational landscape. All of these pathways, ejection from a young solar system, direct collapse from a gas cloud, separation from a binary companion, disruption in a dense cluster, liberation by a supernova, lead to the same destination: a world moving through the galaxy, bound to nothing. And yet, that journey is not entirely without structure. A rogue planet drifting through the Milky Way is not simply wandering at random. It follows a path, a gravitational orbit around the galactic center, shaped by the combined mass of hundreds of billions of stars, clouds of gas and dust, and the dark matter that fills the spaces between. The galaxy itself is a gravitational well, and everything within it moves in response to that, well, tracing long, slow curves through the disk. For a typical rogue planet, one complete orbit around the galactic center takes hundreds of millions of years. That is a span of time difficult to hold in the mind. The Earth has completed fewer than 20 such orbits in its entire history. A rogue planet formed in the early galaxy may have completed dozens, each one a slow arc through regions of varying stellar density, through the arms of the galaxy and the quieter spaces between them, through dust clouds and open voids, always moving, always alone. There is something almost meditative about that image, a world tracing its patient ellipse around the center of the galaxy, passing through everything and belonging to nothing. No star to return to, no fixed point, only the long, slow curve of its orbit and the dark on all sides. Along that orbit, the rogue planet does not move through emptiness alone. The galaxy has texture. There are regions where stars crowd closer together, where the gravitational pull of many suns creates a subtle turbulence in the fabric of space. There are vast molecular clouds, dark, cold, dense, where new stars are being born in slow silence. There are open voids where the nearest light is so far away that even the concept of a neighbor loses meaning. A rogue planet passes through all of these, one after another, over hundreds of millions of years. It does not pause, it does not notice. It simply moves, as it has always moved, following the curve that gravity laid out for it long ago. And yet, for most of that journey, the experience, if we can call it that, is one of profound isolation. The average distance between stars in the Milky Way is roughly 4 to 5 light years. That number is easy to say and almost impossible to feel. 4 light years is about 40 trillion kilometers. It is the kind of distance that makes the word distance feel inadequate. A rogue planet traveling at a typical stellar velocity, perhaps 20 or 30 kilometers per second, would take tens of thousands of years to cross from one star's neighborhood to the next. tens of thousands of years of uninterrupted dark. No landmark, no warmth, no change in the quality of the silence. Most of a rogue planet's existence is exactly that, the long crossing, the patient traversal of a void so large that human timescales dissolve inside it. Occasionally, though, something changes. As a rogue planet drifts through the galaxy, it may, by chance, pass close enough to a star to feel that star's gravity in a meaningful way. Not a collision. The distances involved make that almost impossible. But a gravitational conversation, a slow, subtle pull that bends the rogue planet's path, drawing it into a wide, loose arc around the star. In rare cases, this could amount to a temporary capture. The rogue planet, for a time, becomes something like a planet again, orbiting a sun, however distantly, however briefly. The physics of this is delicate. For a capture to hold, energy must be carried away somehow. Otherwise, the same gravitational interaction that pulls the rogue planet in will eventually push it back out. A third body, another planet, or a passing object can absorb that excess energy, allowing the capture to persist. Without that third body, true capture is extraordinarily rare. But the galaxy is old, and rare things happen, given enough time. Some astronomers have wondered whether our own solar system has participated in such an exchange. The outer solar system, beyond Neptune, in the cold and distant reaches where sunlight is little more than a bright star among stars, is not as well understood as the inner planets. The orbits of some distant objects behave in ways that are not fully explained by the known planets alone. One hypothesis, still debated, is that something large and unseen orbits the Sun at enormous distance. This hypothetical object has been called Planet 9. If Planet 9 exists, and that remains an open question, one possibility is that it did not form here. It may have formed elsewhere, drifted freely through the galaxy for a time, and been captured by the Sun's gravity during a close encounter in the solar system's early history. A rogue planet briefly tamed. A wanderer that found, by chance, a star willing to hold it. It is a quiet thought that somewhere in the outer dark of our own solar system, there may be a world that once knew only the interstellar void and now traces a slow, solitary orbit around a star it never chose. But finding such a world, if it exists, is another matter entirely. Detecting rogue planets is among the most technically demanding challenges in all of observational astronomy. The difficulty is fundamental. These worlds produce almost no light of their own. They reflect no starlight, because there is no star nearby to reflect. They are cold, dark, and small against the vast backdrop of the galaxy. Looking for them is, in a very real sense, looking for nothing, or rather, looking for the faint traces that nothing leaves behind. There is one exception. A rogue planet that is young enough, formed within the last few tens of millions of years, still carries the heat of its own formation. That heat radiates outward, not as visible light, but as infrared radiation, warmth, leaking slowly into the cold of space. The most massive young rogue planets glow faintly in this way, like embers cooling in the dark. And space telescopes built to see infrared light can, in principle, detect them. The Wide-Field Infrared Survey Explorer, known as WISE, was one of the first instruments sensitive enough to find these faint signatures. Scanning the sky in infrared wavelengths, it identified several objects that appeared to be free-floating planetary mass bodies. Cold, dim, moving through space without any apparent stellar companion. Each one a candidate. Each one a world that had been drifting, undetected, until a telescope happened to look in the right direction at the right time. But WISE was only the beginning. The James Webb Space Telescope has brought a new quality of vision to this search. Its sensitivity to infrared light is far beyond what came before, and it has begun finding rogue planet candidates in young, star-forming regions, places where newly formed objects are still warm enough to be seen. The detail it can resolve and the faintness of the objects it can detect have opened a part of the sky that was previously invisible to us. In 2023, Webb turned its instruments toward the Orion Nebula, one of the most active regions of star formation in the galaxy, roughly 344 light-years from Earth. What it found there was unexpected. Among the young stars and glowing gas, Webb detected a population of free-floating objects with masses in the planetary range. Not stars, not brown dwarfs. Exactly. Something smaller, something dimmer. Worlds without suns, drifting through the nebula in the early stages of their existence. And some of them appeared to be paired. Two objects, orbiting each other, with no parent star between them. These paired objects were given an informal name, jumbos, for Jupiter-mass binary objects. The name is a little ungainly, but the thing it describes is genuinely strange. Two planetary mass worlds bound to each other by gravity, moving together through the nebula as a pair, neither one orbiting a star, neither one alone, exactly. And yet both of them adrift in a way that no planet in our solar system has ever been. Their existence is difficult to explain. If rogue planets form primarily by ejection from solar systems, it is hard to understand how two objects would be ejected together in just the right way to remain gravitationally bound to each other. The more natural explanation is that they formed together directly from the gas cloud as a binary pair without ever belonging to a larger system. But that raises its own questions about how such low-mass objects can form through direct collapse. The honest answer is that we do not yet know. The jumbos are a puzzle that current models have not fully solved, and that is, in its own quiet way, a reminder of how early we are in understanding these worlds. The galaxy is full of them, billions, perhaps, each one a world, each one moving through the dark on its own long path, carrying whatever secrets its interior holds, waiting, without knowing, it is waiting, for a telescope to notice the faint warmth it leaves behind. And so the puzzle remains open. The jumbos, Jupiter-mass binary objects, as astronomers have come to call them, are not simply a curiosity at the edge of a catalog. They are a quiet challenge to the way we thought rogue planets came to be. For a long time, the dominant picture was one of ejection. A planet forms, it finds itself in the wrong place at the wrong time. A gravitational encounter with a larger neighbor sends it outward, past the edge of its solar system, into the dark. That story is well supported by computer simulations. It happens often. But two planets, ejected together, remaining bound to each other, that is a much harder story to tell. The geometry alone is difficult. For two objects to leave a solar system as a pair, the encounter that ejected them would need to be extraordinarily precise. Not impossible, perhaps, but unlikely enough that it strains the explanation. The more natural reading is that some rogue planets, perhaps many, never belonged to a solar system at all. They formed the way stars form, from a collapsing pocket of gas and dust, but with too little mass to ignite. And some of them formed in pairs, two objects condensing from the same cloud, settling into a slow orbit around each other before the cloud had fully dispersed. That possibility changes something in how we think about the dark between the stars. It is not only a graveyard of lost worlds, it may also be a birthplace, a place where worlds come into being without ever knowing the warmth of a sun. We are still learning how to find them. The most powerful tool we currently have for detecting rogue planets across the galaxy is not a camera. Exactly. It is a method, a way of listening for the gravitational whisper of a world passing through the line of sight between us and a distant star. It is called gravitational microlensing. The principle is this: light does not travel in perfectly straight lines when it passes near a massive object. Gravity bends it, gently, almost imperceptibly, but measurably. When a rogue planet drifts between Earth and a background star, its gravity acts like a lens, bending the star's light around it and focusing more of it toward us. For a brief time, the star appears to brighten. Then the planet moves on, the alignment breaks, the star returns to its ordinary brightness, and the planet vanishes back into the dark, unseen. The whole event can last anywhere from a few hours to a few days, depending on the mass of the planet and how quickly it is moving across the sky. A more massive planet bends more light and produces a longer, stronger brightening. A smaller planet, something closer to Earth in mass, produces a subtler signal, a shorter flicker in the data. That brevity is itself information. Astronomers can read the duration of the brightening and extract a rough estimate of the lensing object's mass. A signal that lasts only a few hours points towards something small, perhaps Earth-sized, perhaps smaller. For years, a survey called OGLE, the Optical Gravitational Lensing Experiment, has been watching the sky with exactly this kind of patience. It has monitored hundreds of millions of stars, night after night, looking for the faint and fleeting brightenings that signal something passing in the dark. And it has found them. Among the many microlensing events OGL has recorded, several stand out for their brevity. Events so short that the objects responsible would need to be very small, not Jupiter-sized, not even close. Some of the signals are consistent with objects no more massive than Earth. A few may be even lighter. If those detections are confirmed, and confirmation in microlensing is a careful and statistical process, then Earth-mass rogue planets may be among the most common objects in the entire galaxy. Not rare exceptions, not exotic outliers, common. More common, perhaps, than stars. That thought settles slowly, the way large thoughts do. A galaxy filled with dark, Earth-sized worlds, drifting through the space between stars, each one invisible, each one detectable only by the brief shadow it casts on a light we were already watching. The survey work continues, and it is about to expand considerably. A telescope called the Nancy Grace Roman Space Telescope, named for NASA's first chief of astronomy, is expected to bring microlensing surveys to a new scale. Its wide field of view is designed to monitor an enormous number of background stars at once, far more than any ground-based survey can manage. Where OGLE watches patiently, Roman will watch broadly, sweeping across vast regions of the sky simultaneously. The expectation is that Roman will detect hundreds of rogue planet candidates, perhaps many more, through microlensing alone, each one a brief brightening, each one a world that passed through the line of sight and left only a statistical trace behind. There is something worth sitting with in that. Every detection is indirect. The planet itself is never seen. No image is formed. No surface is photographed. No atmosphere is measured. The rogue planet passes through, bends a little light, and continues on its way, entirely unaware that it has been noticed. What we are left with is a number, a mass estimate, a duration, a position in the sky at a particular moment. From that, we infer a world. We say, something was there, something of roughly this size, moving at roughly this speed in roughly this direction, and then it was gone. It is, in its own way, one of the most honest forms of detection in astronomy. We are not seeing the planet. We are seeing the effect of the planet on the light behind it. We are reading the galaxy's shadow play. And yet, each of those shadows is a world. Some of them may be rocky, like Earth. Some may be wrapped in thick ice. Some may carry, deep beneath that ice, a slow ocean warmed by the decay of ancient elements, uranium, thorium, potassium, releasing their heat in the dark, as they have been doing for billions of years. None of that warmth reaches the surface. None of it escapes into space in any form we could easily detect. It simply persists, quietly, in the interior of a world that has no sun, no seasons, no sky worth speaking of, only the long, unbroken night of interstellar space above and the slow warmth of geology below. We find these worlds by the light they borrow from stars they will never orbit. A brightening that lasts a day, a curve in the data, a note in a catalog. And then the dark closes back over them, and they continue on, patient, cold, carrying whatever they carry through a galaxy that is fuller than it looks, and darker than we used to think, and stranger in the quietest possible way than we had imagined. There is something quietly poetic about that. A world announces itself not by shining, but by dimming something else, it passes between us and a distant star, bends the light just slightly, and for a day or two, the star brightens in our data. Then the world moves on, and the star returns to what it was, and the world returns to what it has always been: invisible, unhurried, alone. We never see the planet itself, only the shadow it casts on a borrowed light. And then, even that is gone. These worlds have no day. They have no night, either, not in the way we mean those words. Day and night, as we experience them, are a gift of rotation in the presence of a star. The sun rises because the earth turns toward it. The sun sets because the earth turns away. Without a star, that rhythm simply does not exist. Some rogue planets still rotate. The angular momentum that set them spinning, whether at the moment of their formation or at the moment they were flung free, does not simply vanish. There is nothing in the deep interstellar dark to slow a spinning world. No tidal pull from a nearby star to gradually lock its face in one direction. So some of them turn, slowly, in the dark, completing rotations that no one counts and no one marks. But the turning means nothing. There is no light to rise. There is no light to set. One face of the planet is the same as the other: cold, dark, and open to the stars. If you could stand on the surface of a rogue planet, and setting aside the cold and the airlessness and everything else that would make that impossible, the sky above you would be extraordinary. Stars in every direction, not the washed-out sky of a city, not even the clear sky of a mountain on a moonless night. The full, unfiltered sky of deep space, with no atmosphere to scatter the light, no nearby sun to drown the fainter ones. Thousands of stars visible to the naked eye, and behind them, the soft smear of the Milky Way itself, arching overhead in both directions. It would be, in its way, beautiful. And yet, none of those stars would be a sun. Not one of them would warm your face. Not one of them would cast a shadow at your feet. They would shine as they shine from deep space, brilliant, cold, and utterly indifferent to the world beneath them. They are not your star. They are simply the stars, present, remote, offering light without warmth, direction without meaning. There would be no sunrise, no slow brightening at the horizon, no color bleeding into the sky before the disk appears. No sunset either, no amber, no violet, no moment when the day releases its hold and the night begins. Those transitions require a star close enough to matter, and here, none of them are. There would be no seasons, no year. The planet orbits nothing, so there is no annual cycle, no tilt that brings summer to one hemisphere and winter to the other. Time passes, but it passes without the markers we use to measure it. The only motion in the sky, over very long timescales, would be the slow turning of the galaxy itself, the distant arms wheeling overhead across millions of years, indifferent and immense. Some rogue planets may not travel alone. A world cast out from its solar system might carry a moon with it, or a rogue planet that formed directly from a collapsing cloud might have gathered a companion during that process. The moon would orbit the planet as it always had, held by gravity, tracing its path in the dark. That moon would be lit only by starlight, not the warm, directed light of a sun, but the faint, diffuse glow of 10,000 distant stars falling equally from all directions. It would be a dim illumination, gray, soft, barely enough to cast shadows. The moon's surface would be visible, but only just. A pale, quiet world lit by the collective whisper of the galaxy. And yet that moon might not be as cold inside as it appears. The planet it orbits is massive, and a massive body exerts tidal forces on anything that circles it. As the moon moves through those tidal forces, flexing slightly, stretching and relaxing with each orbit, that mechanical energy becomes heat. Deep inside the moon, rock warms, slowly, persistently, without any star involved at all. This is the same process that keeps Io alive. Io, the innermost large moon of Jupiter, is the most volcanically active body in the solar system, not because of the sun, but because Jupiter's gravity needs it continuously, generating heat from the inside out. Io has no need of sunlight to maintain its volcanism. It has Jupiter. A moon orbiting a rogue planet could have something similar. The planet looming overhead, vast and dark, pulling at the moon's interior with every pass, generating warmth in the rock. Possibly, in the right conditions, maintaining liquid water somewhere beneath the surface. A subsurface ocean on a moon of a rogue planet drifting through interstellar space. The layers of isolation in that image are almost difficult to hold in the mind. And from the surface of that moon, the rogue planet itself would fill a large portion of the sky, not as a bright disk, but as an absence, a vast dark circle, blotting out the stars behind it, its edges perhaps faintly lit by the collective starlight falling on its atmosphere. If it has one, a presence defined by what it obscures, a world known by its shadow, even to its own moon. Not all rogue planets are cold in the same way. The rocky ones, the smaller ones, lose their heat relatively quickly, a few 100 million years, and the surface is as cold as the space around it. But the larger ones, the gas giants, the worlds wrapped in thick envelopes of hydrogen and helium, carry their warmth differently. A Jupiter-sized rogue planet, formed 4 billion years ago, would still be radiating heat today. Not much, by stellar standards. But measurable, the hydrogen and helium that make up its bulk are not merely insulation. Under pressure, hydrogen becomes something close to a thermal blanket, trapping the heat of formation near the interior, releasing it only slowly over geological time. These worlds glow faintly in the infrared, not visible to the eye, but visible to the right instruments. And it is partly this glow that has allowed us to find some of them. Young gas giant rogue planets, still warm enough from their birth to stand out against the cold background of space. They are not warm in any way that would comfort you, but they are not entirely cold either. They carry the memory of their formation in their temperature, and that memory fades only over billions of years. A gas giant rogue planet is, in a sense, still finishing the process of being born, still releasing the energy of its own collapse, slowly into the dark, with no one to receive it. Smaller, rocky worlds do not have this luxury. A rocky rogue planet, something closer in size to Earth or Mars, loses its heat far more quickly. The surface area is smaller, the internal reservoir shallower, and within a few 100 million years, the warmth of formation has largely bled away into space. The planet becomes thermally invisible. No infrared glow, no detectable signature, just a cold, dark sphere, indistinguishable from the surrounding emptiness. This is part of why rocky rogue planets are so difficult to find. They cool, and then they disappear from our instruments entirely, even if they are still there, still drifting, still present in the dark. Mass, in this way, determines much of a rogue planet's fate. The more massive the world, the longer it holds its warmth. The longer it holds its warmth, the more likely we are to find it. A gas giant, with its enormous interior and its thick insulating envelope, persists in the infrared for billions of years. A rocky world the size of Earth fades from view in a fraction of that time. The universe does not treat all worlds equally. Size matters. Here, as elsewhere, and the smallest rogue planets are the ones most likely to drift through the galaxy entirely unseen. And yet, even the gas giants, in their cold isolation, are not entirely still. There is weather on these worlds, not the weather of a sunlit atmosphere, driven by the uneven heating of a star, but something quieter, and in its own way, stranger. Deep inside a gas giant rogue planet, heat rises from the interior. It moves upward through the atmosphere in slow convective columns, cooling as it climbs, then sinking again as it loses its warmth. This circulation, This slow breathing of the atmosphere is enough to organize itself into patterns, bands of cloud, currents of gas moving in opposite directions at different latitudes, perhaps storms, vast and slow, turning in the upper atmosphere with no sun to power them and no season to end them. The clouds on such a world would be unlike anything in our solar system. On Jupiter, clouds form from ammonia and water, shaped partly by the sun's distant warmth. On a rogue gas giant, the chemistry would be different. The temperature's lower, the layers of the atmosphere arranged by internal heat alone, but clouds there would be, layers of frozen particles, suspended in the dark, illuminated by nothing. If you could somehow stand above that atmosphere and look down, you would see only darkness. The clouds would be there, but there would be no light to reveal them. Some of these worlds may be warmer than you might expect. There is a class of rogue planet that theorists have described in careful, measured terms, a world with a thick hydrogen atmosphere, massive enough to hold it, and an interior still warm enough to heat the layers above. In some models, the combination of internal heat and the insulating properties of compressed hydrogen is sufficient to raise the surface temperature above the freezing point of water, above 0 degrees Celsius. On a world with no star, the hydrogen is doing something remarkable here. Under pressure, it does not behave the way hydrogen does in the thin air of Earth's atmosphere. It becomes dense, sluggish, almost liquid in its behavior. And in that compressed state, it traps heat the way a heavy blanket traps warmth. Not perfectly, not indefinitely, but well enough. Well enough that the surface beneath it might be liquid, might be wet. These worlds have a name in the theoretical literature. They are called hydrogen worlds. Warm, dark, and wrapped in a sky so dense it would be invisible to any eye that tried to look through it. The atmosphere would press down with many times the force of Earth's. Standing on the surface, if standing were even possible, you would feel that pressure in every direction, a weight that has no equivalent in ordinary experience. The sky above would not be blue or gray or black. It would simply be there, pressing, opaque, a ceiling of compressed gas stretching upward for hundreds of kilometers. And beneath it, perhaps, water. Not a frozen ocean locked under ice, as we imagine beneath the shell of a rogue rocky world, but open water or something close to it. Dark water, under a dark sky, on a world that has never known sunlight and never will. The surface of such a world would be utterly still. In one sense, no wind driven by solar heating, no tides pulled by a distant moon, and yet the atmosphere above it would be moving, slowly, driven by the heat rising from below. There might be something like rain, condensation falling through the lower atmosphere, reaching the surface, evaporating again. A slow, dark cycle, powered entirely from within. Life on such a world is not something we can rule out. The conditions are extreme by any measure we are accustomed to. High pressure, complete darkness, a chemistry dominated not by oxygen and nitrogen, as on Earth, but by hydrogen and methane. Nothing we know of would thrive there easily, but some researchers have noted, carefully, that hydrogen metabolizing microbes are not unknown on Earth. Organisms that consume hydrogen and produce methane as a byproduct exist in the deep sediments of our oceans, in the guts of animals, in the cracks of ancient rock. They do not need sunlight. They do not need oxygen. They need only a chemical gradient, a difference in energy that they can exploit. On a hydrogen world, that gradient might exist. The chemistry of the deep atmosphere, where heat from the interior meets the cooler layers above, could provide the kind of disequilibrium that life, in its most basic form, knows how to use. This is speculative. The researchers who propose it are careful to say so. But it is not speculation without foundation. It is speculation grounded in what we know about the flexibility of life and the range of conditions it has already learned to inhabit. What this means, quietly, is that the habitable zone may not be a zone at all. For decades, the search for habitable worlds has been organized around a simple idea that life requires liquid water. and liquid water requires a star close enough to provide warmth. The habitable zone is the ring around a star where temperatures are just right. Not too hot, not too cold. Earth sits within it. Mars barely touches its outer edge. But rogue planets do not orbit stars. They have no habitable zone to sit within. And yet, as we have seen, some of them may have liquid water anyway, warm from below, insulated from above, sustained by processes that have nothing to do with starlight. The hydrogen world, if it exists, is a world that the traditional definition of habitability simply did not anticipate. Habitability, it turns out, is less about where a world sits in space and more about what is happening inside it, about the balance between heat generated and heat lost, about the chemistry of the atmosphere and the depth of the ocean and the slow patience of geological time. A world can be warm without a sun. A world can be wet without a star. The universe has more ways to keep a world alive than we first imagined. And rogue planets, cold, dark, solitary, are part of the reason we know that now. So the question of habitability has quietly shifted. It used to rest on a single measurement, distance from a star. How far? How close? How much light falls on the surface? That was the frame. That was the whole picture. But rogue planets have gently dismantled that frame. Not with drama, not with a single discovery that overturned everything, but slowly, through the accumulation of what the physics allows, through the realization that warmth can come from below as easily as from above, that an ocean does not need sunlight to exist, that life, as far as we understand it, needs energy and liquid water and chemistry, and none of those things require a star. Habitability, it turns out, may depend more on what is happening inside a world than on where that world sits in space. The internal engine matters. The atmosphere matters. The slow balance between heat generated deep in the rock and heat lost to the surrounding dark. These are the variables that determine whether a world is alive in any meaningful sense, and they are variables that rogue planets can satisfy quietly in the cold between the stars. This realization has changed how some researchers think about the search for life. For decades, the habitable zone was the map, the narrow ring around each star where liquid water might persist on a surface. Astronomers counted the stars in the galaxy and estimated how many had planets in that ring, and from that they built their estimates of how many worlds might be inhabited. But if rogue planets can also be habitable, even occasionally, even in principle, then the map is incomplete. The dark spaces between the stars are not simply corridors. They are not empty transit routes between the places that matter. They may be places themselves, populated by worlds that have never seen a sunrise and never needed one. The search for life has grown wider because of this. Not louder, not more certain, just wider. And rogue planets are part of the reason. The space through which they travel is not entirely empty. This is easy to forget. The word interstellar suggests a void, a pure and featureless nothing between the stars. But the interstellar medium is a real and complex environment. Thin, yes, sparse beyond anything we experience on Earth, but present. It contains gas, mostly hydrogen, drifting in clouds so diffuse that a cubic centimeter might hold only a single atom. It contains dust, fine grains of carbon and silicate, the remnants of old stars. And it contains something more energetic, cosmic rays. These are not rays in the way light is a ray. They are particles, mostly protons, some heavier atomic nuclei, moving through the galaxy at velocities close to the speed of light. They carry enormous energy. They arrive from all directions, accelerated by supernova shock waves and the magnetic fields of distant stellar remnants. A rogue planet drifting through the galaxy moves through this constant, invisible rain. For a world with no atmosphere and no magnetic field, the surface would be a harsh place. The most energetic cosmic ray particles penetrate rock, break apart molecules, damage the kinds of complex chemistry that life depends on. A bare, unprotected surface would be bathed in this radiation continuously, over billions of years. Surface life, under those conditions, would be unlikely. But some rogue planets may carry a form of protection. Rocky planets can generate magnetic fields through the motion of molten iron in their cores. Earth does this. The result is a magnetic envelope that surrounds the planet and deflects many incoming charged particles, bending their paths away from the surface. A rogue planet with a sufficiently large iron core, still partially molten from its formation heat or from radiogenic warming, could maintain a magnetic field for billions of years. The same slow decay of uranium and thorium that might keep a subsurface ocean liquid could also keep the core warm enough to sustain that protective field. The magnetic field would not stop everything. The most energetic cosmic rays pass through even Earth's magnetosphere, but it would reduce the flux at the surface significantly. It would make the surface a quieter place. And beneath a thick ice shell, the protection would be even greater. Ice is a more effective radiation shield than it might seem. Even a few meters of ice can absorb and scatter cosmic ray particles, reducing the radiation environment below to something far more benign. A subsurface ocean lying beneath kilometers of ice would be almost entirely shielded from the cosmic ray flux above. The ice that traps the internal warmth also filters the radiation from outside. It is a kind of double shelter, insulation below, shielding above. A world that has, without any intention, arranged itself into a place where the conditions for life are at least not immediately hostile. And then there is something else that fills the space between the stars. Something older than any planet, older than any star. The interstellar medium carries a faint background of microwave radiation. It comes from every direction equally. It has no source you can point to, because its source is everywhere. It is the afterglow of the Big Bang itself, still present after nearly 14 billion years, still filling all of space with a whisper of warmth. Astronomers call it the cosmic microwave background. Its temperature is about 2.7 Kelvin, that is 2.7 degrees above absolute zero, the coldest possible temperature. The point at which all thermal motion ceases is 0 Kelvin. The cosmic microwave background sits just barely above that threshold. It is not warmth in any sense that would comfort a living thing. It is the faintest imaginable residue of an event so vast and so distant in time that the light from it has been stretched over billions of years of cosmic expansion, from brilliant gamma rays down to the long, slow wavelengths of microwaves. But it is real. It is present. It touches every surface in the universe, including the frozen surface of every rogue planet drifting through the dark. A rogue planet in intergalactic space, far from any galaxy, far from any star, in the most isolated region of the observable universe, would still be bathed in this radiation from all directions. It would not be alone in that sense. The echo of the beginning would still reach it. There is something quietly extraordinary about that. A world that formed perhaps 10 billion years ago, ejected from its solar system, drifting ever since through the cold and the dark, and still, at every moment, touched by the oldest light in the universe. Not warmed by it, not changed by it in any meaningful way, but present within it, held within the same ancient glow that reaches every corner of space. The cosmic microwave background is cooling. As the universe expands, the wavelengths stretch further, the temperature drops. In the far future, it will fade towards zero. The universe will grow colder and darker, and even this faint background warmth will diminish. But for now, it is there. And the rogue planets drift through it, as they have drifted through everything. Patient, cold, carrying their frozen surfaces and their hidden depths through a universe that is mostly darkness, and mostly silence, and mostly time. And that fading will come. Not soon, not within any time scale that touches human meaning. But the universe is not bound by human timescales. It moves at its own pace, indifferent and unhurried, And in its deepest future, even the faint warmth of the cosmic microwave background will thin toward nothing. The rogue planets will still be there when it does. Most of them, at least. Their fate is tied to the fate of everything, to the slow unwinding of the universe itself. And that unwinding is patient beyond imagining. Over trillions of years, the radioactive elements inside a rogue planet will decay. Uranium, thorium, potassium, the quiet furnaces that have kept these worlds warm since their formation, will exhaust themselves. One nucleus at a time, the heat they generate will diminish. Slowly at first, then more completely, the subsurface oceans, if any existed, will cool. The ice above them will thicken. The last liquid water will freeze. And the planet will grow still. Not all at once. These things happen across timescales so vast that the current age of the universe, nearly 14 billion years, would be a brief opening chapter. But eventually, the internal warmth runs out. The geology quiets. The last tremor fades. What remains is a cold, dark, inert sphere. A world that was once, in some sense, alive with process, now simply drifting. A fossil world. That phrase carries something true in it. A fossil is a record of something that once moved, once changed, once participated in the chemistry of a living system. And a rogue planet, in its final state, is something like that, a record of conditions that no longer exist, preserved in cold and silence, moving through a universe that has grown emptier around it. Not all rogue planets will reach that quiet end in the same way. Some will be captured by black holes. A rogue planet drifting too close to one of the galaxy's many stellar mass black holes, or to the supermassive black hole at the galactic center, will follow a path it cannot escape. Slowly at first, then faster, drawn inward along a curve that ends in compression and heat and dissolution. A world that survived billions of years of cold solitude ended in moments. Others will be flung outward. A close gravitational encounter with a massive star or with another dense object can transfer enough energy to send a rogue planet beyond the galaxy entirely, out past the last stars, out past the halo into the intergalactic void, where the darkness is deeper. The distances between anything are measured in millions of light years, and the cosmic microwave background is the only company left. A small number will fall into stars. After billions of years of solitary travel, a rogue planet's path will intersect with a stellar system, and it will spiral inward, or strike directly and end in a brief, bright dissolution of heat. The solitary journey concluded in fire. There is something almost restful in that image, not violent, just final. A long, cold thing, briefly warm again, at the very end. But most will do none of these things. Most will simply continue. Drifting on, growing colder, growing quieter, for timescales that have no comfortable analogy. The age of the universe is roughly 14 billion years. The timescales over which rogue planets cool to inertness are measured in the trillions, and the timescales over which the galaxy itself disperses, over which black holes evaporate through Hawking radiation, over which the last structures dissolve. Those are longer still, by factors that language struggles to hold. The rogue planets will be there for most of it. Patient in a way that nothing else quite matches. They do not wait for anything. They carry no expectation of rescue, no orientation toward a star that might one day warm them. They simply persist, because persistence requires nothing of them, cold and dark and moving, through a universe that is itself growing cold and dark and still. There is something in that which is difficult to name, not sadness. Exactly, more like a recognition of scale, of how much of the universe is simply endurance, matter continuing to exist, to move, to occupy space long after any warmth has left it. Rogue planets are, in a sense, the most patient objects in the cosmos. They wait without knowing they are waiting. They endure without choosing to endure. They are simply there, in the dark, in the cold, in the long silence between one moment and the next trillion years. And we have only recently learned that they exist at all. The first confirmed rogue planet candidate was identified in the late 1990s. It was found in a young star cluster called Sigma Orionis, a loose gathering of newly formed stars in the constellation Orion, roughly 1,000 light-years from Earth. Among the faint infrared signatures of young stellar objects, astronomers noticed something that did not fit, an object too cool to be a star, too warm to be invisible, drifting without any apparent parent. It was designated S-Ori 70. Its mass was estimated at somewhere between 3 and 7 times the mass of Jupiter, a wide range, reflecting the genuine uncertainty in the measurement. But even at the lower end, it was a substantial world, larger than anything in our solar system, drifting freely through a cluster of young stars with no star of its own. The discovery was quiet, as most astronomical discoveries are: a paper, a designation, a set of measurements. But the questions it raised were not quiet at all. Was S-Ori 70 a planet, or was it something else? The debate that followed was not merely about naming. It touched something deeper, the question of what a planet actually is, and whether that category is defined by what an object is made of, or by how it came to be. A planet that formed in a disk of gas and dust around a young star, and was later thrown out by gravitational interactions, has a fundamentally different history than an object that collapsed directly from a cloud of gas, the way a star does, but without enough mass to ignite fusion. Both might end up as free-floating worlds of similar size. Both might look identical in an infrared survey, but their origins are different in kind, not just in degree. One is a world that was made in the warmth of a solar system and lost it. The other never had a star to begin with. That distinction matters to astronomers trying to understand how planetary systems form, how often they eject their members, and how the galaxy's population of free-floating objects came to be. It matters for the models, for the statistics, for the larger picture of how worlds are made and unmade across cosmic time. And yet, from the outside, the two objects look the same: cold, dark, drifting, carrying their histories inside them in ways we cannot yet read. The International Astronomical Union has not drawn a clean line between rogue planets and the lowest mass brown dwarfs. The boundary remains soft, contested, a region where categories blur and nature declines to simplify itself for our convenience. That ambiguity is not a failure of science. It is an honest reflection of how the universe actually works. Objects do not sort themselves into the bins we prepare for them. They exist on continuums, in gradients, in the spaces between our definitions. S-Ori 70 sits in one of those spaces, neither fully one thing nor fully another. A world at the edge of categories, drifting through a cluster of young stars, carrying a question that has not yet been fully answered. And in that, it is perhaps more representative of rogue planets than any tidy definition could be. Worlds at the edge of things. Between the stars, between the categories, between the warmth and the cold, patient and dark, and quietly present in a universe that is mostly the same. And yet, for all that ambiguity, the science does not stand still. Astronomers have learned to work within the uncertainty to gather what evidence they can and hold their conclusions gently. One of the most productive places to look has been the Orion Nebula. It lies about 344 light-years from Earth, close enough, by galactic standards, to study in some detail. It is one of the most active star-forming regions in the sky. Thousands of young stars are scattered through it, in various stages of formation, some still wrapped in the gas and dust from which they condensed. It is a place of beginnings. And within it, astronomers have found something unexpected. Dozens of free-floating planetary mass objects, drifting through the nebula with no star to call their own. They are detectable there for a reason that would not apply to older rogue planets elsewhere in the galaxy. They are young enough that they still carry the warmth of their formation. When a world condenses from a collapsing cloud of gas and dust, the process releases energy. That energy becomes heat, and the heat takes time to radiate away. For a very young object, that residual warmth glows faintly in infrared light. Not visible to the eye, but readable by the right instruments. The James Webb Space Telescope, with its extraordinary sensitivity to infrared wavelengths, has been able to pick out these faint warm signatures against the luminous backdrop of the nebula. And what it found there has quietly unsettled some assumptions. Among the free-floating objects in Orion, a subset appeared to be traveling in pairs. Two objects, orbiting each other, with no parent star between them. They were given an informal name, jumbos. Jupiter-mass binary objects. Their masses ranged from roughly half a Jupiter mass at the lower end to about 13 Jupiter masses at the upper. A wide range, spanning the uncertain boundary between planet and brown dwarf. But it was not their masses that drew the most attention. It was the fact that they were paired. Two worlds bound to each other by gravity, drifting together through the nebula. No star, no system. Just the two of them, in a slow, mutual orbit, moving through a cloud of gas and newborn suns. This is difficult to explain. Current formation models, whether they describe ejection from a solar system or direct collapse from a gas cloud, do not naturally produce binary pairs of free-floating objects in significant numbers. Ejection, almost by definition, is a solitary process, a planet flung outward alone on an escape trajectory, leaving its companions behind. Direct collapse can produce binary systems, but the conditions required to form two low-mass objects bound to each other without a larger stellar body nearby are not well understood. One hypothesis is that the jumbos formed as wide binary pairs directly from the gas cloud itself, two condensations that collapsed in proximity, close enough to become gravitationally bound before either had fully formed. A kind of twin birth in the dark of the nebula before any larger structure had claimed them. Another hypothesis reaches toward the complexity of the cluster environment. In a dense region like the Orion Nebula, gravitational interactions between many bodies happen frequently. Multi-body encounters can produce unexpected outcomes, objects flung into new orbits, pairs formed from previously unrelated worlds, configurations that no simple two-body model would predict. It is possible that some jumbos were assembled, in a sense, by the chaos of the cluster. Two objects that formed separately, brought into a mutual orbit by the gravitational geometry of a crowded environment. Neither hypothesis is fully satisfying. Neither has been ruled out. The jumbos remain, for now, a question that the data has posed and not yet answered. And that question has a quiet implication that extends beyond Orion. If binary rogue planets exist there, they likely exist elsewhere. The Orion Nebula is not unique. It is simply close enough and young enough for us to see what is happening inside it. Other star-forming regions, scattered across the galaxy, have presumably produced similar populations of free-floating objects. Some of those objects may also be paired. The discovery of jumbos has prompted a careful reassessment of how common binary rogue planets might be across the galaxy as a whole. And that reassessment has a numerical consequence. The estimates of rogue planet populations that existed before the jumbos were based largely on the assumption that free-floating worlds travel alone. If even a small fraction of them have companions, moons, binary partners, loosely bound satellites, then the total number of free-floating worlds is higher than those estimates suggested. Perhaps significantly higher. Each binary pair counts as two worlds, not one. Each rogue planet with a moon is a system, however small and dark. The galaxy, already thought to contain billions of these wandering objects, may be fuller still. There is something worth sitting with in that thought. Not the numbers themselves, which are too large to feel, But the image they suggest, pairs of worlds drifting through the dark between the stars, bound to each other by nothing but gravity. No light from outside, no warmth from a sun. Just two masses circling slowly in a silence that has lasted since before our solar system formed. They do not know they are together. They do not know anything, but they persist in their quiet orbit, carrying the fact of each other through the interstellar dark for timescales that have no human equivalent. The youth of the Orion objects is also scientifically useful in another way. For young objects, the relationship between luminosity and mass is better understood than it is for older ones. A young world that is still warm radiates in a predictable way, and from that radiation, astronomers can estimate its mass with more confidence than they could for a cold, ancient rogue planet detected only by microlensing. This makes Orion a kind of calibration ground, a place where the properties of free-floating worlds can be studied more directly than almost anywhere else. The masses of the jumbos, ranging from half a Jupiter to 13 Jupiters, span the very region where the classification debate is most active, where planet shades into brown dwarf, where formation history becomes ambiguous, where the categories we have built begin to soften at the edges. And so Orion brings us back, gently, to the same place that S. Ori 70 brought us, to the recognition that the universe does not resolve its own ambiguities on our behalf. It offers us objects and light and the faint infrared signatures of warmth. It offers us brief brightenings in the data and paired worlds drifting through nebulae. And it leaves the interpretation to us. We build our categories carefully, and the universe fills them imperfectly, and that imperfection is not a problem to be solved. It is the texture of reality, pressing back against the smoothness of our models. The jumbos are part of that texture. Warm, young, paired, unexplained, moving through the Orion Nebula at this very moment, as they have been for millions of years, as they will continue to do long after the nebula itself has dispersed and the stars within it have scattered across the galaxy. Patient, as rogue planets always are, and quietly, persistently present. And so we leave the Orion Nebula behind. We leave its warmth, its young stars, its paired and puzzling jumbos drifting through clouds of gas that still glow with the light of formation. We move outward into the quieter spaces, into the long dark between things, where rogue planets travel alone, and where, very rarely, two of them find each other. The galaxy contains billions of these worlds, as far as we can tell. And yet, even billions, spread across a structure 100,000 light-years wide, amounts to an extraordinary thinness. The average distance between rogue planets, even assuming the highest estimates of their number, is still measured in light-years. Not kilometers, not astronomical units, light-years. The distances that take light itself years to cross. So when two rogue planets do encounter each other, it is an event of almost incomprehensible rarity. A coincidence written in the grammar of orbital mechanics, playing out over timescales longer than the history of complex life on Earth. Such an encounter would not look like a collision in any dramatic sense. There would be no explosion, no flash of light visible across the galaxy. Just a slow, quiet curving of paths. Two dark worlds, each traveling its own ancient trajectory, each feeling the other's gravity as a gentle insistence. A pull, a deflection, a bending of the line each had been following for perhaps billions of years. They would approach and curve, and in most cases separate again, each continuing on a slightly altered course, carrying the memory of the encounter only in the new angle of their drift. This is what gravitational interaction looks like at its most patient. Not violence, but geometry. Not destruction, but a slow negotiation between masses. In rare cases, the geometry resolves differently. Two rogue planets, approaching on trajectories that leave no room for separation, would merge. The collision itself would be slow by human standards and catastrophic by any other. Two worlds, each perhaps the size of Earth or larger, pressing into each other over hours or days. Rock and ice and compressed gas folding together under forces that reshape continents in moments. And in that merging, gravitational energy, the energy of two masses falling toward each other, would be released as heat. The combined body would warm, not to the temperatures of a star, not even close, but warm enough, briefly, to melt what had been frozen for billions of years. A temporary thawing in the long cold. A world that had been dark and still suddenly lit from within by the energy of its own making. And then, slowly, the heat would dissipate. The new, larger world would cool again, settling back into the patient cold from which it had briefly emerged, carrying within it the compressed record of two separate histories, now inseparable. Some of the rogue planets drifting through the galaxy today have been drifting for a very long time. The first stars formed roughly 13 billion years ago, not long, in cosmic terms, after the Big Bang. And the processes that produced rogue planets began almost as soon as planetary formation began, which means the oldest rogue planets have been traveling through the dark for something close to 13 billion years. They predate our Sun by nearly 9 billion years. They were already ancient when the cloud of gas that would become our solar system had not yet begun to collapse. But those oldest worlds would look very different from the rocky planets we know. The early universe was a simpler place, chemically speaking. In the first moments after the Big Bang, only the lightest elements existed in any abundance: hydrogen, helium, and traces of lithium. The heavier elements, carbon, oxygen, iron, silicon, the elements that build rock and metal and the molecules of life, did not yet exist in meaningful quantities. They had to be made, and they were made inside stars. In the cores of massive stars, over millions of years, nuclear fusion built heavier and heavier elements from lighter ones. Carbon from helium, oxygen from carbon, silicon, sulfur, iron, in a slow accumulation of complexity. And when those massive stars died, when they exhausted their fuel and collapsed and exploded as supernovae, they scattered those elements outward into the interstellar medium, seeding the galaxy with the raw materials for a new kind of chemistry. The first rogue planets, formed before many supernovae had enriched the galaxy, would have had almost none of those heavier elements. They would have been gas worlds, vast, cold spheres of hydrogen and helium with no solid surface to stand on, no rock beneath the ice, no iron at the core. Worlds without geology in any sense we would recognize. Drifting, enormous, featureless. Later generations of rogue planets tell a different story. As billions of years passed, and star after star lived and died, and scattered its elements across the galaxy, the interstellar medium grew richer. Molecular clouds, the dense regions of gas and dust from which new stars and planets form, accumulated carbon and oxygen and silicon in slowly increasing proportions. And the rogue planets that formed from those enriched clouds could be rocky, could have solid surfaces, mineral compositions, the layered interiors of differentiated worlds, could, in principle, be something like Earth, cold and dark and airless, but built from the same periodic table. There is something worth sitting with in that progression. The chemical composition of a rogue planet is not arbitrary. It is a record, a frozen sample of the interstellar medium at the time and place of the planet's formation. A gas-dominated rogue planet tells you it formed early, when the galaxy was young and heavy, elements were scarce. A rocky rogue planet tells you it formed later, after generations of stars had lived and died and given their substance back to the galaxy. Each world carries within it a kind of chemical timestamp, a signature of the conditions that existed in one particular corner of the Milky Way at one particular moment in its history. If we could ever retrieve a piece of a rogue planet, a fragment of its crust, a sample of its ice, we would be holding something extraordinary. Not just a rock, a record, a direct sample of the interstellar medium from billions of years ago, preserved in the cold and the dark, untouched by the chemistry of any star system, unaltered by the warmth of any sun. It would tell us things about the early galaxy that we currently can only infer from models and from the light of distant objects. It would be, in a sense, a message from the deep past, written not in words, but in isotope ratios, in mineral structures, in the quiet arithmetic of atomic bonds. No mission to retrieve such a sample has ever been seriously proposed. The nearest rogue planet candidates are still light years away. And light years, for now, remain beyond us. But the thought of it is worth holding for a moment. Somewhere in the dark, a world is drifting that formed when the galaxy was young. It has been traveling for longer than the Earth has existed. It carries within it the chemistry of a time we have never seen and can barely imagine. And it asks nothing of us. It simply moves. Cold and patient and full of a history it will never tell. And yet, for all the quiet wonder of that thought, the distance remains. Light years are not a poetic abstraction. They are a physical fact, and they are, for now, absolute. The nearest rogue planet candidates we have identified are still several light years away, not close in any sense that matters to a spacecraft, or to a human lifetime, or to many human lifetimes placed end to end. The fastest object humanity has ever launched is the Voyager 1 probe. It has been traveling for nearly 50 years and has only just crossed the boundary of our own solar system. At that speed, reaching the nearest star, not a rogue planet, just the nearest star, would take roughly 70,000 years. A rogue planet, drifting somewhere in the dark between stars, is not a destination we can reach. Not yet. Perhaps not ever, with the tools we currently possess. No serious mission proposal has ever been drawn up. Not because the idea lacks appeal, but because the arithmetic of distance and time closes the door before the conversation can begin. We can dream of it. We can calculate what such a mission would require, but the numbers do not resolve into anything buildable, not in any near future we can honestly envision. So we watch from here. And watching, it turns out, is not nothing. There is another way a rogue planet might come to us, or at least come closer. Not close enough to visit, but close enough to notice. If a rogue planet were to pass through the outer reaches of our own solar system, it would leave traces, gravitational traces. The outer solar system is home to vast populations of small, icy bodies, the scattered disk, the Kuiper belt, and beyond that, the Oort cloud, a vast and diffuse shell of frozen objects extending perhaps a quarter of the way to the nearest star. A rogue planet moving through that region would tug at those objects as it passed, gently, over long timescales, but persistently. The orbits of distant bodies would shift. Some would be nudged inward, toward the sun. Others might be flung out into deeper space. The pattern of those disturbances, if we could read it clearly enough, would carry the signature of whatever passed through. Some researchers have looked for exactly this kind of signature. They have examined the orbital distributions of outer solar system objects, searching for clustering or anomalies that might point to a past encounter with something large and dark and unannounced. So far, no conclusive evidence has emerged. The data are suggestive in places, but not definitive. The search continues, quietly, as surveys of the outer solar system grow more complete and more precise. It is patient work, the kind of work that may take decades to resolve. The idea of a rogue planet passing through the inner solar system, through the region where Earth and the other familiar planets orbit, is sometimes raised. It surfaces in popular discussion from time to time, usually with more alarm than the physics warrants. The probability of such an encounter is vanishingly small. The solar system, for all its apparent fullness, is almost entirely empty space. The distances between planets are vast. Even a rogue planet traveling on a direct trajectory through the inner solar system would, in all likelihood, pass through without striking anything at all. The geometry simply does not favor collision. What it does favor, over long timescales, is subtler. Gravity reaches further than any physical impact. A rogue planet passing through the outer solar system, even at considerable distance, could perturb the Oort cloud in ways that take millions of years to fully unfold. Those perturbations could dislodge comets from their distant, stable orbits and send them falling inward toward the sun. A slow rain of comets, arriving over thousands of years, redistributed by the gravitational wake of a world that passed and is long gone. This process has been proposed as a possible driver of mass extinctions. The idea is that periodic or irregular increases in comet flux could deliver impacts to the inner solar system, with consequences for life on Earth. It is a hypothesis that has been discussed seriously in the scientific literature, but it remains speculative. No specific extinction event in Earth's history has been definitively linked to a rogue planet encounter. The evidence needed to make that connection, a clear orbital signature, a timing that matches a source that can be identified, has not yet come together. It may never come together. Some questions about the deep past are simply beyond the resolution of the tools we have. And so rogue planets remain, in this sense too, at the edge of what we can know, close enough to affect us, perhaps distant enough to remain invisible, present in the data as a possibility, but not yet as a fact. The study of these worlds does not belong to any single branch of science. It sits at a crossing point. Planetary science contributes the understanding of how worlds form and evolve. Stellar astrophysics provides the context of how stars and clusters shape the environments in which planets are born and sometimes lost. Astrobiology asks the quieter question underneath all the others, whether any of this matters for life, whether the dark and the cold and the isolation are truly prohibitive or merely challenging. Each discipline brings its own tools. Infrared telescopes to catch the faint warmth of young rogue worlds still glowing from their formation. Gravitational surveys to detect the brief, silent passage of a planet across a distant star's light. Atmospheric models to ask what a thick hydrogen sky might do to the temperature of a world with no sun. Geophysical simulations to trace the slow decay of radioactive elements deep inside a rocky body, and the heat that decay releases, and what that heat might mean for water, and for chemistry, and for the conditions that life, as far as we understand it, requires. None of these tools, alone, is sufficient. The field is genuinely interdisciplinary in a way that is not merely organizational, but necessary. The questions are too large and too varied for any single framework to hold them, and the field is young. Many of its most important questions are still open in the most fundamental sense, not awaiting better data, but awaiting the right data, which has not yet been collected, from instruments that in some cases have not yet been built. There is something appropriate about that. Rogue planets are themselves unfinished stories, worlds that formed and traveled, and are still traveling. Their histories are not concluded. Their interiors are still slowly cooling. Their orbits are still slowly curving through the gravitational landscape of the galaxy. We are catching them mid-journey, and we are, ourselves, mid-journey in understanding them. The questions we are asking now, how many are there? How did they form? Could any of them be warm enough, wet enough, sheltered enough? These are the early questions, the ones that come before the answers, the ones that define the shape of a field still finding its footing. It is enough, for now, to know that the questions are real, that the worlds are real, that somewhere beyond the reach of any spacecraft we have built or imagined, a planet is moving through the dark, carrying its frozen surface and its hidden interior through a galaxy that does not notice it and does not need to. It moves because it has always moved. It drifts because that is what it does. And we, from our small warm world around our ordinary star, have only just begun to learn that it is there. And so the questions remain, not as failures of understanding, but as the natural shape of a young field, a field that has only recently learned to ask the right things. How many rogue planets exist in the Milky Way? The honest answer is that we do not know. Not approximately. Not within a comfortable margin. The uncertainty spans orders of magnitude. There could be billions. There could be many times more than that. The surveys we have conducted have sampled only a narrow slice of the galaxy, across a narrow range of masses, using methods that are themselves still being refined. Every new telescope, every new survey revises the estimate, and the revisions have not yet converged. What fraction of rogue planets formed by ejection, and what fraction collapsed directly from gas clouds? Current data cannot yet tell us. The two populations would look nearly identical from a distance. A world thrown out of a solar system and a world that formed alone in the dark would both appear as cold, dim, drifting objects. Their origins are written in details we cannot yet read. The chemistry of their interiors, the isotopic ratios in their rocks, the faint signatures of a formation disk that may or may not have once surrounded them. These are the clues, and we have not yet found a way to gather them. Do any rogue planets harbor liquid water? There is no direct evidence. None. We have never observed a subsurface ocean on a rogue planet. We have never measured the temperature beneath one's ice shell. We have never detected the chemical signatures that might hint at liquid water in the dark. And yet, the physics does not forbid it. That is not a small thing to say. The physics of radioactive decay does not care whether a planet orbits a star. Uranium decays at the same rate in the dark as it does in the light. Thorium does not require sunlight to release its heat. The interior of a sufficiently large rocky world will stay warm for billions of years, regardless of where that world happens to be. And a thick shell of ice, pressing down from above, would hold that warmth in, would keep the water liquid, would create, in the deepest dark, a place where chemistry could continue. We have seen this work. Europa carries a liquid ocean beneath its ice, warmed not by the sun, but by the tidal pull of Jupiter. Enceladus vents water vapor from cracks in its frozen surface, fed by an ocean that has no business existing so far from any star. These are not hypothetical worlds. They are real, and they are in our own solar system, and they have been there for billions of years. A rogue planet is colder than either of them, more isolated, more alone. But the principle is the same. Internal heat is internal heat. It does not require a star to exist. Could life exist on a rogue planet? The honest answer is that we do not know. And that uncertainty, that genuine, unresolved, carefully held not knowing, is itself a kind of wonder. It means the question is still open. It means the universe has not yet told us no. Life on Earth began in darkness, in the deep ocean, far from sunlight. The earliest ecosystems we know of were built not on photosynthesis, but on chemistry, on the energy released when hot mineral-rich water meets cold seawater at hydrothermal vents. No light required, no star required, only heat and water, and the slow, patient work of chemistry over time. A rogue planet with a subsurface ocean and an active seafloor would have all of those things. The heat would come from below. The water would be there, held liquid by pressure and insulation. The chemistry would proceed, as chemistry always does, without asking permission. Whether that chemistry could ever cross the threshold into life, whether it has, somewhere, already, we cannot say. The origin of life is not yet understood even on Earth, where we have the most evidence. On a rogue planet, we have none. But the universe is under no obligation to confine life to the warm circles around stars. It never made that promise. We assumed it, because stars were the only warmth we knew to look for. Rogue planets suggest that warmth can come from within, that a world does not need to orbit anything to be, in some quiet sense, alive with possibility. The dark spaces between stars are not simply empty corridors. We have thought of them that way for a long time, as the gaps between the real places, as the nothing between the somethings. But rogue planets move through those spaces, billions of them, perhaps, each one a world, each one carrying its own history, a formation in a disk of gas and dust, perhaps a long orbit around a young star, perhaps a gravitational encounter that sent it spinning outward into the dark, or perhaps a direct collapse from a cold cloud, a world that never knew a star at all. Each one has a surface, each one has an interior, each one has been somewhere and is going somewhere and has been doing so for longer than our sun has existed. They do not know they are alone. None of them know anything at all. There is no awareness there, as far as we can tell. No experience of the cold, no sense of the passing time, no recognition of the stars that wheel slowly overhead. They are not lonely in any way that matters to them. Loneliness requires a mind, and these are just worlds. And yet they persist. Cold, dark, patient in a way that has nothing to do with patience, because patience also requires a mind. They simply continue, moving through the galaxy on paths that were set before our sun ignited, before our solar system condensed from its cloud of gas and dust, before the Earth existed, before anything we know existed. There is something quietly humbling about a world that has never seen a sunrise, and never will. It has no morning. It has no seasons. It has no year, because a year is a measure of time around a star, and there is no star. There is only the slow orbit around the galactic center, taking hundreds of millions of years to complete, passing through regions of varying density and gravity, drifting through dust clouds and open space with equal indifference. It carries its frozen surface through all of it and its hidden depths. The ice above, the possible warmth below, the long silence in between. The light we see when we look at the night sky is the exception. The dark between the lights is the rule. We are drawn to the stars because they are visible, because they announce themselves, because they warm us and orient us and give us something to navigate by. But the stars are islands, and the ocean between them is vast and dark and full of things that do not shine. Rogue planets are part of that darkness, not an absence, a presence, a quiet, cold, patient presence that we have only recently learned to look for, that we are only beginning to find. And somewhere out there, not metaphorically, but actually in the physical space between the stars, a world the size of Earth is moving through the dark. It has been moving for billions of years. It will continue moving for billions more. It does not know we are here. But we are beginning to know that it is there, and that, in the long silence of the universe, is something. And so we find ourselves here, at the edge of what we know. The telescopes are improving. Slowly, steadily, they grow more sensitive, more patient, better at listening to the faint signals that the dark gives up, only reluctantly. And as they improve, we find more of them. Not by seeing them directly. A rogue planet in deep interstellar space gives off almost no light. It does not announce itself. It does not call out. It simply moves, as it has always moved, through the space between the stars. What we find instead is a shadow, a brief brightening in the light of a distant star, a star that has been quietly burning for billions of years, its light traveling across the galaxy toward us. And then, for a few hours or a few days, something passes between that star and us, something dark, something massive enough to bend the light around it, to focus it, to make the star appear for just a moment, slightly brighter than it was. And then it passes, and the star returns to its ordinary brightness. And the rogue planet continues on its way, indifferent, unknowing, carrying its frozen surface and its hidden depths back into the dark. That brightening in the data, that small, quiet curve on a graph, is a detection. It is not a photograph. There is no image of the world itself, only the evidence of its passing. only the shape it left in the light of something else. There is something worth sitting with in that. A world that has been drifting for billions of years, formed, perhaps, in the early chaos of a young solar system, flung outward by the gravity of a larger neighbor, crossing the boundary between bound and free, and then traveling for billions of years through the dark. And we find it by the shadow it casts on a star it will never orbit. Each detection is a small acknowledgement, a quiet recognition that this world existed, that it passed through this particular corridor of space at this particular moment in cosmic time, that our instruments happened to be watching, that the geometry happened to align. Most rogue planets will never be detected at all. They will drift through the galaxy for the entire remaining life of the universe and never once pass in front of a star that anyone is watching. Never once bend the light in a way that reaches a telescope. Never once leave any trace in any record. They will simply be in the dark, alone. And yet the numbers suggest they are everywhere. The galaxy is fuller than it looks. When you look at the night sky, you see the stars, you see the bright points, the familiar patterns, the slow arc of the Milky Way, if the sky is dark enough, and it looks like a place defined by light, by the presence of suns. But the light is the exception. Between every star and every other star, there is an enormous volume of space that contains almost nothing. Almost. Because scattered through that space, in numbers that may exceed the stars themselves, are worlds. Dark worlds, cold worlds, worlds with no sun to warm them, no seasons to mark the passage of time, no sky that ever brightens. The dark is populated, not densely. The average distance between rogue planets, even if billions of them exist, is still measured in light years. A rogue planet is profoundly alone in any practical sense. It will never come close to another world. It will never be touched by the light of a nearby star. But it is there. And it is not nothing. It has mass. It has gravity. It has a surface, however frozen. It has an interior, however dark. It carries within it the chemical record of the molecular cloud from which it formed, the isotopic ratios of elements that were forged in stars that died before our sun was born. It is a geological archive, a silent record, moving through the galaxy on a path that began before our solar system existed. And somewhere in that vast, dark, populated space, there is a world the size of Earth. Not a gas giant, not a massive object still glowing from its formation, a small, rocky world, roughly the size of the one you are lying on right now. It is moving through the space between the stars. It has been moving for billions of years. Its surface is cold beyond easy imagining, around minus 240 degrees Celsius, cold enough that any atmosphere it once had has long since frozen and settled onto the ground as a thin layer of frost, cold enough that the surface is silent and still and dark in a way that no place on Earth has ever been. But beneath the surface, beneath the ice, there may be warmth, slow warmth, quiet warmth, the warmth of radioactive elements decaying in the rock below, uranium and thorium and potassium, releasing their energy in tiny increments over billions of years, warming the rock, warming the water above the rock, keeping something liquid in the dark. A hidden ocean, covered by ice, surrounded by nothing, moving through the space between the stars in complete and total silence. No light reaches it. No signal from any civilization has ever touched it. It does not know we exist. It does not know anything. And yet it persists. The water moves, perhaps slowly. Currents driven by the heat from below. Minerals dissolving from the rock. Chemistry happening, as chemistry does, wherever the conditions allow. Whether anything lives in that water, whether anything has ever lived in that water, we do not know. We may never know. The honest answer is that we cannot say, but the physics does not forbid it. And that is a thought worth carrying gently into sleep. That somewhere in the dark between the stars, in the cold, in the silence, there may be something, not a civilization, not a light, not anything that would recognize us or reach toward us, but something small and patient and alive in the deep, unaware of the galaxy turning slowly above its frozen ceiling, unaware of the stars, unaware of us, just present in the dark. The galaxy moves. The rogue planet moves with it. Billions of years have passed. Billions more will pass. And somewhere between the stars, a world drifts on. In the cold, in the quiet, in the long, long patience of